Okay, last week we started on highway vertical alignment, and today we are going to continue with that. Uh, the vertical alignment it's composed of a group of vertical tangents, okay, connected with vertical curves. If we, look at the natural shape of the ground. Okay, you will see it irregular shape like this one, for example. So this the natural ground level. Okay, of course this way it's irregular shape, and it has ups and downs and stuff like that. Our typical cars are not designed to drive on such rough terrain. So basically what we look for smooth ride. So how can we do that? We can, either make a smooth ride like this, okay, or we even can go more and do something like this. Okay, forgive me, this is supposed to be a straight line. Okay, so why we don't go with this option? Why we don't go with this option? Basically, what prohibits us from going with this option is the amount of fill that we are gonna make here. So here, for example, that was a level of plus 232, and this point is at a level is 215. So the volume that we need to fill here is huge. We have almost 17 meters depth. Filling a 17 meters depth is not an easy job, because we have to do it on layers and make a quality control check to make sure that it's compacted, okay, before we paving the road. And here we are gonna cut. The height of the cut is huge. So when we are trying to make our vertical profile, we try to do the following. We try to minimize the cut and fill. So this option is not a valid option. So we try to go with, a more practical and acceptable way. So in order to do that, we try to keep our cut and fill to the minimum, or to at the least. So here, for example, we try to do something like this. Okay, so we build here this profile such that the amount of cut and the amount of fill, first of all, are balanced. Okay, and the maximum height for cut and the maximum depth is acceptable. Okay, we try to avoid more. So the depth for fill, for example, less than or equal 2 meters. Okay, if it's 1 meter, that's better even. Okay, and so on. You get the point? So the subject to maintaining level of, but the slopes here, we try to maintain it at an acceptable grade level. The acceptable grade level is basically less than or equal 8% grade level. Sometimes in mountainous area, we are faced with 12% or even 15%. But we try to minimize these extreme grades. And here the grade should be comfortable for passengers and suitable for vehicles. For vehicles, if you are driving on a grade that is 5% upgrade, A passenger car, this is, an easy ride for them. You don't feel it. But for trucks, this is a heavy grade. This grade is a challenging grade for heavy vehicles. Okay? Any questions so far? So, as we mentioned here, for passenger cars, for most cars, the range of 4 to 5% grade does not affect performance or loss in speed. For trucks, the story is different. The effect of grades on truck speed is much more significant. And here we have the highway capacity manual chart. That's the vehicle performance curves for trucks, okay, of 120 kilograms per kilowatt. Okay. How you can calculate this? For example, if you have an 18-wheeler that weighs, or it has a 50 tons, and it has maybe an engine that has 500 horsepower. So how can we find this? So it's 50,000, 50, okay, 1,000 kilograms divided by 500 multiply 1.8 by 1.35, I'm sorry, to convert it to kilowatt. So here you will have 5,000, 50,000 divided by 500 divided by 1.35. So we have here 74 kilogram per, per horsepower. Okay, I converted the horse per kilowatt, I converted the horsepower by multiplying it by 1.35 to be kilowatt. Okay, so we had an example last week on how to use these charts, and we will use it later extensively. So the vertical alignment, the critical length of grade for design, using the maximum grade, it's is not the governing factor, but basically the length of the grade also. As we mentioned here, you can have a grade of 8%, but if that grade is for maybe for 200 meters, so the drop in speed, if the truck is entering at 90 and it drives up to 200 meters for a short grade length, the drop will be here. The exit speed will be almost 64. But if this grade exceeded 800 meters, that's going to be the exit speed. The speed will drop to almost 24 kilometers per hour. As you can see, the length of the grade, not just the degree of the grade, no, also the length. It plays a major role for the speed impact, or the impact on the speed of the vehicle. Also, the entrance speed, or the speed at entrance in that critical length, grade length, is important. So here, for example, if a vehicle is entering the grade at 70 and drove on that grade for maybe 200 meters, so this horizontal distance is 200 meters. Actually, the distance from here to here is 500. As you can see, the exit speed will be significant. So the entrance speed plays a major role. The length of the grade plays a major role. And what is the third? The drop in speed on the critical length. The allowable drop on that critical length. All of these three are major factors for the critical, or for the designing the grade of the highway. Here, that's a vertical. That's a critical length of grade for design, and it shows that the drop in the speed. Okay, that's a speed reduction. That's for the 25 kilometers per hour speed reduction. Okay, and that's the percentage upgrade. So you can get from here, and that's the length of the grade. It gives you exactly what is the maximum length. For example, if you are if you're having a 5%, okay, and the length of the grade in meters 15, okay, 1500, and for example that grade was 5%, so the drop is going to be almost 25 kilometers per hour. But if the grade was 500, so we are going to be here. The expected drop is 15 kilometers per hour, and so on. There's a very important, due to this impact on the speed, usually in the vertical alignment, we create what is called climbing lane. What's the purpose of the climbing lane? Climbing lanes are basically for trucks, because as we mentioned before, the impact of the grades on trucks is more pronounced. So if we have a two-lane highway, and going up, going on an upgrade, okay, if there's a truck, it's gonna drop in the speed and it's gonna block the road. So that's why we create a special lane, we call it climbing lane, for the trucks to drive through. If any one of you drove on the Al-Aqaba in the south up to Abha, okay, you will find if you are going uphill, you will see that there is two lanes at some point. These are climbing lanes. So that's the main lane for the traffic, and the other lane, that's climbing lane for trucks. Okay. For example, here, if you have a condition like this one, we have up, vertical curve like this. So we will have a climbing lane for the direction coming from here. Okay, and it's going to end right here, and there's a climbing lane on the other side for that direction, as you can see here. Any questions so far? Okay, the criteria for designing a climbing lane. That's very important subject. When do we need to design or to add a climbing lane? Okay, if the upgrade traffic flow rate is greater than 200 vehicles per hour. Okay. So that's the first condition. We have to satisfy these three conditions. The upgrade truck flow, okay, or the number of trucks is at least 20 trucks per hour. Okay, then one of the following conditions applies. The speed drop is 15 kilometers per hour or greater than 15 kilometers per hour. There is a drop in the level of service from E to F. The level of service drop is 2 levels or more. Okay, so if any of these conditions applies, then at this point we must add a climbing lane. Clear? Okay, so for the given grade segment of two-lane highway, determine if a climbing lane, okay, is needed or not. If needed, please determine its start and end facts. Okay, the facts is we have a grade 8%, and the volume is 650. Truck percentage Okay, and okay, it seems that there was a graph here, but it's missing. So that's the grade, that's 8%, and that's the distance. Okay, and that was the volume, 650. Truck percent is 5%, and the design speed is 90. And the question here, okay, determine if a climbing lane is needed or not. Let's make our check. Upgrade volume is 650. This is not kilometer per hour. This is vehicle per hour. So we have 600 vehicle per hour. That's the traffic volume. So we satisfied the first condition, that the upgrade traffic flow rate is greater than 200. So this one is greater than 200. Number of trucks, we have 5% trucks. So we have 0.05 multiply 650. So this would be 0.05 multiply 650. So that's 32.5 trucks. That's greater than 20. Okay, then from the chart we need to determine the drop in the speed, if there's a drop in speed, or there's a drop in the level of service, or there's a level of service drop from E to F. In this case, we go and use this chart. Okay, this chart, it says that, you know, if there's a drop below the 15, then we must add a climbing lane. So let's see, in our case, we have an 8% upgrade, and the length of the grade is 300 meters. So let's go here and try to solve the problem. So let's start with a ruler. Okay, before we start with the ruler, let's identify the horizontal distance. As we mentioned, our grade is 300 meters. So here we have how many units? Okay, so here we have 1, 2, 3, 4, 5, 6, 7, and a fraction. So we have 7 multiply 2 plus 1 and multiply 0.3, or in this case is going to be 0.6. So we take 5 units, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the mark for the 300 meters. So now let's just mark our stopping point, or the exit point. So that's the exit point. It's going to be here. What does this mean? This means that the truck will enter here at 90 kilometers per hour, then will drive horizontally this distance. I'm sorry, let me just It's going to drive here horizontally for 300 meters, which match this point. So when it will exit at this speed. So the exit speed, that means the truck is entering here at 90 kilometers per hour. When it finish the upgrade, okay, here, this 300 meters, and this is 8%. When it exits with this speed, which is, I think, 53 kilometers per hour. It will exit with 53 kilometers per hour. So how much was the speed drop? The drop in speed is 90 minus 53, so that's 37 kilometers per hour. 37 kilometers per hour, which is greater than 15 kilometers per hour. The 15 kilometers per hour is here. So as I mentioned before, anything under this line, then we must add a climbing lane. Given that the volume and the truck the percentage of trucks or the number of trucks conditions are satisfied. Okay, so in this case we need to add okay, let me just take this out. Let's put the ruler again. Now we agree that we need to add a climbing lane, but the question now, where to start the climbing lane? So that's the line that marks the drop 15 kilometers per hour drop. After the 15 kilometers per hour drop, then we must add a climbing lane. So the climbing lane is going to be starting right here at this point. Okay, at this point, so this segment must have a climbing lane. So it starts here. Just ballparking here, that's, I think, this distance approximately. You can also use the scale, but I'm gonna just say approximately this is almost 100 meters. That means the starting of the climbing lane is going to be here. So the climbing lane will be only in this segment. And it starts here after 100 meters. Okay. Now, where does it end? Okay. It ends, assuming this was a flat segment, 0%, it ends when the speed of the truck reaches at least 75 kilometers per hour. So let's go back and see when it exits, when the truck exits at this point, it enters the zero slope. So the zero slope is this curve. It needs a distance to accelerate. So that's the curve that we will try to. So now it's going to enter at this point at 0 grade. Okay. And that's the point when it's going to end. When it reach at this point, the speed of the truck is 75 kilometers per hour. Okay. So how much is this distance from here between these two. This looks like 600 meters. So this will continue here. So it will continue for 600 meters after, ending the sharp grade. This is to allow the truck to accelerate to reach to the 75 kilometers per hour. We are not looking for the truck to accelerate to 90, no, but this is the acceptable level. That the drop is, 15 kilometers per hour. Okay? One of you might ask me, Doctor, why we bother about this drop in speed? I will tell you something. The drop in speed is not only for capacity purpose, it's for safety also, because if there's high, if there's the variations in speeds between vehicles on the highway is high, that creates a very volatile condition for accidents. Okay? Any questions so far? Okay, let's go back to our slides. So here we solved this example and we identified where to start and where to end the climbing lane. Now we go to the vertical curves. These are the curves that connect between these grades. If we have two grades like this, so we need to have a curve to connect between both of them. So we have two types of vertical curves. We have a crest curve, okay, and we have a sag curve. So this is a sag curve, this is a crest curve. This is type 1, that means you have a positive grade and negative grade on one side, and sometimes you have two positive grades, okay, but the second grade is less than the first grade. Or you have two negative grades and the second grade is, greater than the first grade, and so on. Remember that in the vertical curve, the story is different. It's different than the horizontal curves. The horizontal curves, it was a circular part of a circle, but here it's different. It's basically a parabola. Okay, so let's just so here the vertical curve follows this equations. Okay, the elements of the vertical curve, we have a point of vertical curvature, VPI, vertical point of, and there's a vertical point of intersection. Okay, vertical point of curvature, vertical point of tangent here. Okay, we have an approach grade, that's the G1, and we have G2, and we have length of the curve in meters. So the length of the curve, the horizontal length, equal to the curvature length. Okay, so the rate of change of grade, R, is G2 minus G1 over L. Then there's the equation of the curve is y of x. As I mentioned, it's a parabola, second degree formula, ax squared plus bx plus y naught, where a is basically equal r over 2. This r over 2. Okay, G2 minus G1 divided by 2L. And B is G1. And Y node, okay, that's the elevation of the VBC. So these are, so in other words, you can write it this way. Y of X equal G2 minus G1 over 2L multiply x squared plus G2 multiply x plus elevation, okay, of VBC. Clear? This will give us the elevation for any point on the curve. Okay. Any questions so far? Okay. So what are the geometric characteristics? Okay. Here for the shown curve, determine stations and elevations for VBC and VBI and BVI. The station and elevation for the highest point. Let's try to solve this example. So we have this point, the PVT station and elevation. Okay, and the length of the curve is 270 meters. So what is the station, okay, of the BVI? Equals the station of the BVI basically equals the station of the BVT minus this grade multiply L over 2. So this is G1, this is G2 minus, or in this case because it's minus, so it's minus, it's plus G2 multiply L over 2. So here it will be I'm sorry, I'm getting now the elevation, not the, so it's minus L over 2 equals 2 plus 431.05 minus L over 2, which is 135. So here 5, 0, and here 6, 9, 2 plus 2. So this is the station of the BVI. So what's the elevation of BVI? Equals the elevation of this point. Okay, so plus this height. So it's basically the elevation of the BVT, okay, minus G2 multiply L over 2. So here we have 236.62 minus G2 is minus already, so we have minus 0.0365 multiply 135, which is L over 2. So we have 236.62 minus minus, which means plus 0.0365 multiply 135. So here is going to be plus 241.55 meters above mean sea level. Okay, usually the elevations, shabab, is above mean sea level. Okay, so that was the first part for the BVI. We can do the same for the BVC. For the BVC, it's gonna be like this. Let's just try to move this. For the BVC, the situation is similar. We can do the same. BVC equal the station of BVT minus L. So here it's 2 plus 431.05 minus 270.00. Here we have 50.1 and here 6 and here 1. So that's the station of BVC. What's the elevation for BVC? BVC equal the station of the BVI minus this station, minus this distance. This, the difference here. So it's basically elevation of BVI minus G1 multiply L over 2. So here it will be the value that we got here, 241.55 minus 0.0155 multiply L over 2, 135. So this way it will be 241.55 minus 0.0155 multiply 135. So this is going to be 239.45, actually 6, because it's 75 meters above mean sea level. Any questions so far? So this way we answered this part. Now the second question is the station and elevation for the highest point on the curve. How can we do that? We're going to take a break now, and after the break we're going to solve it. Okay?
Okay.
Okay, in the previous part we answered this part, that we got the stations and elevations for both the point of vertical intersection and the point of vertical curve. Okay. Now the second requirement, which is to get the station and elevation for the highest point on the curve. So where or how can we get that? So we are basically looking for this point. We need to get this distance x, so we can get the station, and we need to identify the highest point. So how can we get the highest point on this vertical curve? First of all, the equation of this curve is defined as following. Y of x equal a x squared plus bx plus y naught. So in order to get the highest point, let's get the first derivative of this function. Y dash of x is going to equal 2ax plus b. That's the grade, or that's the slope of this function. So we have this parabola. If we want to get the maximum point, we need to get the point where the grade here is 0. So at the highest point, y dash of x equal 0. That means y dash of x maximum height equal 2ax x max plus b equals 0. That means X maximum equals minus B divided by 2A. So what's B? So let's substitute in this. Let's first calculate A. A equal G2 minus G1 divided by 2L. So we have here G2, it's minus 0.0356, I'm sorry, 0.0365 minus G1, which is 0.0155 divided by 2 multiply 270. So A equals minus 0.0365 minus 0.0155 divided, okay, divided by 2 divided by 270. So this will be minus 9.6296 multiply 10 to the power minus 5. B equal G1. So here X max equal minus G1 is 0.0155 divided by minus 9.6296 multiply 10 to the power minus 5 equals. So here it says plus 160.96 meters. So that means the highest point is the X for the highest point is gonna be at 160 meters from the starting point, okay, from the beginning of the curve. So the station, let's just make a sanity check. Let's use the A that we got and the G, and let's check on Y, the elevation of the BVT. Okay, the BVT, the X for the BVT is going to be L. In this case, where we want to check to make sure that our coefficients are correct. So we need to get the elevation at this point. You get the point? So here X for the BVT. X BVT, which is basically the L. So we are going to do this minus 9.6296 multiply 10 to the power minus 5 multiply 270 square plus 0.0155 multiply L, which is 2, or X is 270, plus Y node, which is basically the elevation of the BVC. So that's the elevation 239. That's the elevation of the BVC, 239.46. So let's see how much this is gonna be. Oh, okay. I see. Now we did a mistake in this equation here. We are supposed to divide it by 2, but here we put only A. So here we need also to divide by 2. So this must be divided by 2. So actually X maximum will be 80.48 meters. That's correct. This is 160. This is wrong. So let's do a check here. So this will be minus 9.6 exponent minus 5 multiply 270 square. This is going to be minus 6.9984 plus 0.0155 multiply 270. So this plus 4.185 plus 239.46. So this will be plus 239.46 minus 6.9984. 236.64 meter above mean sea level. The value here is 236.62. So we have an error of 2 centimeters, which is acceptable. So that means our equation and coefficients are correct. So that's the X. As I mentioned, we did a mistake. We forgot to divide here by 2. So this should be 160.96 divided by 2. So this X should be 80.48. So the station, okay, of maximum height will be the station of point of vertical curvature plus X max. So it's going to be, what was the station for the BVC? It's here. So this is 2 plus 161.05 plus 80.48. So here is going to be 35.142 plus 2. So this is the station for the maximum height. That was the first requirement. What is the elevation at the maximum height? So elevation at, or the maximum elevation, you can say it, max elevation is going to be at X max. So Y max equal minus 9.6296 multiply 10 to the power minus 5 multiply X square, X max square, which is 80.48 square plus 0.0155 multiply 80.48 square plus 239.46. So this will be minus 9.6296 to the power minus 5 multiply 80.48 square plus 0.0155 multiply 80.48 plus 239.46. So this is going to be 240.08 meters above mean sea level. Any questions so far? Okay, then we're gonna stop here and